Our next speaker this morning is Kelpis, who's joined us this summer from College of the Canyons. Brandon's been working with Sten, and today he'll tell us about their project together, Dark Matter Annihilation in M31.
Hello, everyone. Dark Matter Annihilation in M31. Let's talk about it. Okay, so excess gamma radiation has been detected from M31 recently, and we think dark matter is responsible for this. Why is that important? Why does that matter? Well, before I get into the precise details, I kind of want to start with a general context of dark matter so we're all on the same page. So it is theorized to make up 80% of our universe and be completely invisible. Well, if it's completely invisible, how do we theorize it's there in the first place? Well, it's because of its gravitational influence. So Vera Rubin was the first one to observationally discover this. Essentially, she was observing M31, and as she was zooming out from the center of M31, these orbital velocities, some orbital velocities started increasing rather than decreasing. And what this is indicative of, at least for one of the explanations, is that there must be some sort of invisible matter that's responsible for it. And that invisible matter later got coined as dark matter. So dark matter prompt cusp, this is another important facet of my research. So imagine we're in the early universe, we're looking out at this dark matter, it's starting to coalesce, has a smooth density field, but when we zoom in on that smooth density field, there's actually local maxima in this density field. And it is at these local maxima where it starts to gravitationally collapse on itself, and at the point of highest density, it forms these objects called dark matter prompt cusps, which is physically represented right here. The darker colors, like the yellow and the green, that's representing the density. These dark matter prompt cusps are theorized to be like up to 2,000 astronomical units in radius. It follows a power law, its density that is, where its density is proportional to its radius to the negative 1.5. And another important key thing about these dark matter prompt cusps is that we hypothesize, if I can get this GIF playing, that the dark matter particles within the prompt cusp come into contact with each other, annihilate, and give off gamma ray radiation. And also another important characteristic about these prompt cusps is that they're very sensitive to stellar encounters and tidal poles, meaning when they face one of these disruptions, its annihilation luminosity is greatly dampened. And I'll talk about that more in the next few slides. For this slide, what I got right here is a movie created by Sten Delos of prompt cusp formation. It's pretty much going to summarize everything I said just in the previous slide, but add more of like a visual aspect to it. Okay, so what we want to pay attention to right here is this blue curve. This is representing the cusp formation. And as we are decreasing in radius, we are getting more dense. It's following that power law I was just talking about. And then at the point of highest density, we have that cusp formation. And if you're wondering what this T is right here, it's a time scale. It's a cosmic time scale divided by the time of the cusp formation. So when the ratio is equal to 1, we have that cusp formed. Okay, so what is exactly the goal of this summer? As I mentioned in the previous slides, there has been excess amounts of gamma ray radiation detected from M31. And that's shown by this graph right here by Carmen et al., where it's the gamma intensity as a function of angle from the center of M31. Whole lot of stuff going on in this graph right here, but what we want to pay particular attention to are these observed measured intensities, these red bars right here. So these are observationally measured, and what we plan to do is to simulate cusp formation and its distribution throughout M31, and the halos as well, and their annihilation signals, and compare it to the observed measured intensities. And if they match, it shows that the model works for other galaxies other than the Milky Way. I'll get more into that in the next slide. And that ultimately it leads into much more insight about the nature of dark matter. So how are we going to do all this? Well, Jan Stucker made code publicly available online called cusp encounters. Now within cusp encounters, it simulates cusp formation and halo formation and their annihilation signals. Initially, the code comes built for the Milky Way. It's the purpose of the code is to explain the galactic center access of our own galaxy in the Milky Way, the excess gamma ray radiation that is. But dark matter annihilation should be the same throughout the universe. So we're going to go inside that code and alter the parameters to fit M31s. And essentially, when we're going through and altering all those parameters, we're going to make graphs with those altered parameters and used observed analytical fits of galactic components obtained from Tam et al. And make that graph as well and do a plot overlay of the two to ensure that our altered parameters in the code match the observational analytical fits to ensure accuracy, essentially. Okay, so what's the first step in doing this? Well, it's generating a mass map. This is crucial because if we understand the spatial distribution of the cusp, we can simulate, if we understand the spatial distribution of the galactic components, then we can simulate its cusp and annihilation signals. And that's exactly the purpose of this graph right here, which is the total mass enclosed in solar mass units as a function of radius in kiloparsecs. So these are the galactic components right here, such as the stellar disk, the bulge, and the baryons, which in this case is the summation of the bulge and the stellar disk, and then our NFW halo, which is surrounding the galaxy, enclosing it, and then our total curve, which is the summation of everything. We didn't include the other galactic components, such as galactic nuclei or a gas disk, because its mass is so negligible in this instance that it wasn't going to significantly alter our results at all. Okay, as you can see right here with these galactic components, the curves flatten out. That's because at far enough out radii, the total mass enclosed has reached its maximum limit. So if we keep going, the total mass enclosed is going to stay the same. And then also these curves are cut off at the virial radius for M31, which is around 213 kiloparsecs. It might be hard to see, which is a good thing, but this is actually a plot overlay of the observational analytical fits from Tam et al. And then the altered parameters of our code. And basically what this depicts is that our altered parameters and in the code match the observational fits, which is a good thing. Okay, let's talk about halo properties. Now, there's many dark matter models for halos. Excuse me, got that tongue twisted. There's many dark matter models and density profiles. So what we wanted to ensure is that when we're altering the parameters within the code, is that we want to make sure that we're fitting the observational analytical fit of the dark matter halo in M31. And one way to do that is to plot the total orbital velocities as a function of radius, total meaning all those galactic components I had just shown in the previous slide. And when we initially did this, we did not actually get a fit in the total orbital velocities. And we were sure about our galactic components being correct for instance, like the stellar disk and the bulge. So we knew that this mismatch was due to the halo. So going inside the code, we were altering its parameters, such as the mass, which is generally accepted to be anywhere between 1 to 2 times 10 to the 12 solar mass units. And then its initial concentration, which is basically its density during formation, how dense it is towards the center. So after altering these parameters, we were able to get a fit in our total orbital velocities, which is indicative that we're using the correct halo properties. So kind of the same logic here, but with the stellar disk, and the properties we were altering were the scale length and the thickness. And one way to do that is just plot a density contour. Initially, we had a mismatch, so altering the thickness and the scale length, we were able to get a match in our density contour. Not only does that ensure that we're using the correct properties, but it also shows that the 3D mass distribution matches and not just the spherically averaged radial distribution. I just also want to note one other thing. We did not perform the same analysis for the bulge because in the observational analytical fits, the bulge is assumed to be spherically symmetric, and as you can see with the stellar disk, it's more ellipsoidal in nature. Okay, now that we have the parameters out the way, we can kind of get to the fun stuff, such as the annihilation, and that's exactly what this graph is right here. It is the annihilation per spatial volume as a function of radius, and then we got the NFW halo and then the cusps, so I'll kind of go curve by curve here. So we got the NFW halo dominating the annihilation signal at smaller radii, and that's because its annihilation is proportional to rho squared, which is its density. So at smaller radii, we're getting much more dense, therefore its annihilation signal is going to dominate at these smaller radii. Next up, we got this green curve, which are the unperturbed cusps. As I was saying in the earlier part of the presentation, is that these prompt cusps are particularly very sensitive to stellar encounters and tidal poles. Their annihilation luminosity gets dampened. So it makes sense that this red curve right here, which accounts for the stellar encounters and the tidal poles, is in fact weaker in the annihilation signal. And basically, we can apply that same logic to the blue curve, which is accounting for the tidal poles. I also want to emphasize that this is not actually happening when we're at smaller radii. We're towards the center of M31, where there is a bunch of disruption events. So it's more of to show the magnitude of what these disruption events cause to the prompt cusps. And so at 8 to 9 kiloparsecs, we start to see that the prompt cusp starts to dominate the annihilation signal. And then when we are out at further out radii, these three curves, the cusp curves start to converge. That might seem counterintuitive at first, but when we are out at far enough out radii, we are facing much less stellar encounters and the tidal poles are becoming much less intense. So they're not as disturbed as much. That's why the three curves converge. Okay, so for our final results, this is kind of what we've been working towards we have been working towards the entire summer, is the gamma intensity as a function of angle from the center of M31. So now we're going to compare these curves to the observed intensities of carbon et al. Before I go to the next slide and show you the comparison, I just want to emphasize that I put this in a scale right here to where the curves are easier to see and understand. So when I go to the next slide, I'm going to match carbon et al. Scale. So the curves are going to look a little bit different, but they are the same. Okay, so here we see the graphs side by side. So I just wanted to kind of bring up carbon et al.'s graph again to compare the two. Yeah. Yeah, so now I'm going to put the measured intensities on top of my graph so we can see if the prompt cusps are in fact responsible for these excess gamma ray emissions. Okay, so yep, so we got the gamma intensity as a function of angle from the center of M31. These are our measured intensities. These are the measured intensities from carbon et al. And as you can see, it seems that the NFW halo nor the cusp, any of the cusps, seem to be totally responsible for the excess measured intensity, excess gamma ray radiation coming from M31. So this leads me to my conclusion here, is that the prompt cusps are most likely not responsible for the excess gamma ray radiations of M31. There is one caveat to this. For example, we don't know if carbon et al. Was accounting for the gamma radiation coming from our own galaxy when we are observing M31, because we're not exactly on, we're towards the edge in our Milky Way, but we still have radiation when we're looking at M31. And we also don't know if carbon et al. Accounted for the radiation that's coming from behind M31. So that is one caveat to this research. We could arbitrarily just boost the annihilation signal, but as I said earlier in the presentation, is that this model of the code was meant to explain the galactic center excess of our own galaxy. So if we were to boost this annihilation signal, then we would have to boost the excess gamma ray radiation coming from our own galaxy, basically not matching the observed data for the Milky Way. So this graph, our final results indicate that the prompt cusps are in fact not responsible for the excess gamma ray radiations coming from M31. And I'll leave these conclusions up while I take some questions.
Do you know why the measured intensities are like a step function versus your normal? Is it like a function of the measurement?
What do you mean by step function?
Like instead of sloping, it's just like two.
Yeah, because I think this is just because it's taken from like the Fermi telescope. I don't think it's literally that precise. That's why carbon et al. Is pretty much like just like a straight graph, and then we have that cut off towards the second one. So I think it's just because like it's not exactly curve-like. It's yeah. Yeah, I misunderstood something, but in like the animation you had playing with like at the beginning, where you show like the power to the formation of the prompt cusp and then yeah. Why is the density following the power law if it doesn't appear spherically symmetric? That's a great question. I think it's just from the simulations that we have. It just seems to follow that power law, at least with the model that we're using. I wouldn't be sure about exactly what it has to do with like the spherical symmetry. Yeah.
I was a little confused by your results on the final slide when you mentioned what exactly in that graph is, because I think I saw the exact same color. So what are you saying is the thing that you plot?
Yeah, so these are the measured intensities, the ones with the arrow pointing to the red bar. So if I can kind of go back. Yeah, so from carbon et al., these are the observed measured intensities from M31. And these are the same graph. It's the gamma intensity as a function of angle. And we just simulated the annihilation signal of the prompt cusp on the right graph. So if we put the observed intensities, because the whole point was to see if the annihilation signals matches the observed intensities. So if we put the observed intensities from carbon et al. On our graph, we see that the annihilation signal is too weak to account for the measured intensities. Does that make sense?